Today we're going to be talking about the BioBricks Pubchem brick. The Pubchem brick serves compound data from Pubchem, and eventually it will serve bioassay and RDF data. So this is where you can find the repo for the Pubchem brick. It's a work in progress, although you can install it today, and I'll show you that. And this is where the data is coming from. So if you go to the F2P directory for the National Library of Medicine, if you go to Pubchem, you can go to compound, current full, and SDF. And this is the data we're going to be pulling today and looking at. Okay, so let's get started. We're going to start by installing Pubchem. So to install Pubchem, all you need to run is BioBricks install Pubchem. If you don't have BioBricks yet, you can install it with BioBricks with pip install BioBricks. I already have that. And yeah, so let's go ahead and install Pubchem. On my machine, it's going to check, and it's going to find that Pubchem's already installed. Pubchem is pretty big. So in future videos, we'll be showing how you can work with really big bricks. We're just going to do it the slow way today. But the download's going to take a while if you install it and you don't have a really fast connection. But it does all install in one go. And if you have any problems, please ping us. So yeah, let's get started. I guess what we're interested in describing today is what is actually in that brick. And that brick is growing. As I mentioned before, it currently has the compound SDF data, but it will eventually have bioassay data and RDF data. So these are the packages we're going to use today. We're going to use BioBricks just to actually pull the data, tidyverse to do some table manipulations, ggplot2 to build a simple plot, and TikTok just to demonstrate that some of these things can take a long time because we are talking about quite a lot of data here. Okay, so let's go ahead and run that. Pacman is a package that loads packages, and I like it more than having lots of library statements. That's the main reason I use it, but it'll also install the package if you don't already have it. So the first thing we want to know is, like, how do we load Pubchem? And that's really easy with BioBricks. So we just do BioBricks bb load, and Copilot already has it for us. So let's go ahead and load that. And you can see that right now, this brick only has one asset. Pretty soon it's going to have two more assets, the bioassay asset and the RDF asset, but this is all it has right now. And you can see that this asset is made up of 731 different files. And those files are pretty big. So we do PC dollar files. Oops, sorry. So we're going to do PC equal to PC Pubchem, or no, compound SDF, and that's going to set our variable to this one asset that exists in the Pubchem brick. Okay, so we have it now, and you can see that file system dataset, and yeah, so you can see there are a bunch of files there. If we're curious, we could say, you know, how big are those files? And oh, well, these are all symbolic links on my machine, but these files are about 200 megabytes each, I can tell you from memory. So so we've pulled the BioBricks data now. The first question we might ask is, you know, how many rows are in that data? And let's go ahead and divide it by billion, and you'll get 3.7 billion rows. So there's a lot of data in the compound SDF files. You might be saying, hey, aren't there only like 100 million compounds on Pubchem? And just to show you that, you know, if we go to Pubchem, we can see today they're listing 115 million compounds. That's right. I assume they're about right about this number. We'll check it out later. But the reason there's, you know, almost 4 billion rows is because each of these compounds has quite a few properties. And so this is going to be a long form table, but showing is better than telling. So let's go ahead and just take a glimpse of the data. So we're just going to take the top of the data, and to do that, we can do a head, let's say 100. We're just going to collect that, and we'll make it into a tibble. And this might take just a minute. Yeah, there we go. Shouldn't take too long. It should just be reading from the top file in the list. But yeah, so there you go. So you have an ID, and that's actually the compound ID. You have a Pubchem compound ID, so this property for this ID is always going to be the same as the ID column. But you can see there are a bunch of other properties in there too. So in fact, if we were curious, we could say, you know, of these top 100 rows, what are the properties? And we can say option next dot options next dot print equals 100. Try that again. Okay, so the thing we're going to look at today is molecular weight, just because it gives us like a good example of something we can build a plot of this giant data. But I just want to mention, you know, if we weren't sure that these were all the properties, we could go back to the FTP, and eventually this will be part of the Pubchem brick too, using the normalized schema definitions that we'll have part of BioBricks. But yeah, if you go to the FTP in Pubchem, you can see specifications, and then you can see SD tags. Yeah, that's it. And yeah, so you can see all the properties that are available here, specifically the compound properties. So Pubchem molecular formula, Pubchem molecular weight. There we go. So we're interested in molecular weight. Let's go ahead and pull some of that data. So get molecular weights. And this is going to take a while because we're going to have to iterate through all 9 billion lines. There's no index in this Parquet file or anything like that. And in this case, Geb Copilot is not being super helpful. I think that's right. And yeah, so we're going to define the query here, and this is all using the arrow package. So let's go ahead and make sure we have the arrow package loaded in here, although usually I call arrow directly. But basically, PC is a file system data set, and we're going to filter it by this property, but nothing's actually going to happen until we call the collect function. So collect, we used it up here when we were collecting the top of that giant file system data set. But in this case, we're going to add a few different manipulations of the data before we collect it. So you can see that, you know, I still, like, there's no computation happening here. And we're going to do a few other things. So we're going to take the molecular weight table, and in this case, we're going to say the value. So if we take a look at that PC top again, if we take a look at PC top and we filter to property is equal to Pubchem molecular weight, we can see that, yeah, so the values are characters, but they're numerics in this case. So we're going to go ahead and say as the numeric value. And then just because we're sort of interested in averages in this case, we're going to want to group by something. And we have, you know, supposedly we have 115 million compounds. So we don't have to make like big buckets for our molecular weights if we want to count molecular weights. So we're just going to make everything into an integer. So there we go. And then for our next step, we're going to group by value, so the new integer value, and then we're going to summarize, and we're going to say count is equal to n, and that's it. So after that, we'll collect this whole thing. So if we're curious what this is going to do, we can do it on a sample up here. So on our head sample, and let's make the head sample a little bit bigger. Shouldn't take too long to compute that, but let's give it a second. Okay, so now we have a few more molecular weights in here. And instead of using the whole file system data set, let's just take the top, and we don't have to do any collection on this because this is in memory right now. So, you know, the first thing that happens here is that we're filtering down to molecular weight. You see a bunch of molecular weights on the right. And the next thing that's happening is we're mapping those molecular weights to integers. And the next thing that happens is that we're grouping by those integers and we're just counting them. And so, you know, unsurprisingly, on a sample of 1,000, you have usually, you know, one of each possible molecular weight of each molecular weight in that 1,000 sample. So yeah, if we just arranged by negative count, you know, odds are they're all going to be 1. Okay, so there's 2, yeah, 2s. Okay, so that's what's going to happen when we run this. But like I said, it's going to take a while, and that's why we pull TikTok, because we want to time exactly how long it takes. We're not going to compare that to anything today, but in the future, we'll compare that to running this on Spark on a computing cluster and show you that you can really do some interesting things when you take big data and scale it up on big clusters. So let's go ahead and run this. That looks right. Okay, it's going to run. I'm going to pause, and you'll come back when it's done. Okay, and it's done. Looks like it took about 10 minutes on this machine, which is a good machine, but not like a cluster of computers or anything. Probably take you on a good machine about the same amount of time. Okay, so what we see here is we have a table called MW now that has counts and values, and those values are molecular weights, and those counts are the number of compounds that had that molecular weight. So the first question we might ask is how many molecular weights? And this should be close to the number of compounds on Pubchem. So if we do just the sum of all of the counts, you can see that looks like 114 million to me. So total divided by 1E6. Yeah, so 114 million, that's remarkably close to what Pubchem says they have, 115 million. So I would guess they're just rounding. So that's great. That's a nice confirmation that we actually got all the data and, that things are working. So if we're going to plot this, the max value, the max molecular weight that we see, it's probably pretty big. That seems crazy to me, but today we're not going to look into that. So we're only going to visualize the top 99%. So if we want the top 99%, we can arrange by the molecular weight, and then we can find a cumulative sum. Nice job, Copilot. And yeah, so this would actually be the percentile. And that looks good. So let's see how quick that is. Pretty quick. Great. And so if we want the top 99, all we have to do is filter to percentile greater than 99, 98 in this case. And we don't need collect anymore because this is already in memory. But yeah, so MW99, let's take a look at the head. And sure enough, molecular weight of about 1,324, 99% of compounds have less than that molecular weight. And so let's just go ahead and pull value and take the first value. So MW99 is that 1,324 value. So now we're going to create a plot. So for that plot, we're going to create a new data frame, and we're just going to filter the old data frame by value is less than MW99. There we go. And I think we're probably good. So yeah, let's go ahead and do a ggplot, and we're going to save that into G. X is equal to value, Y is equal to count. So we have value and count here, as saw before, and then we're just going to do a gem call. And that should pretty much do it. So yeah, we'll go ahead and save that as a PNG. We would want to manipulate that a whole bunch first. Before we, published or anything, but yeah, so this is basically what we want. Okay, so we have our data frame, and we have our plot, just a bar plot with molecular weights and counts, and yep, and now we're going to save it, and there we go. Okay, so there's kind of like a weird behavior going on here. I don't know exactly why that is. Maybe someone who knows more about this stuff could, maybe someone who has more time to think about it or knows more about this stuff could tell me why there's like this, every other molecular weight has a much higher count. Looks like it's every other one, evens and odds. I don't know. Anyways, kind of interesting. That shows you how to pull the compound SDF data and how to build a basic plot. So if you like this, go ahead and like the video. If we get enough likes, I'll show you how you can analyze the bioassay data from Pubchem, how you can get and analyze it. And then we'll do the RDF data as well. So that's it for today. Thanks for watching. Goodbye.